this video, we're going to be answering the question in the description box. It reads as follows. Two identical small charged spheres, each having a mass of 3 times 10 to the power of negative 2 kg, hang in equilibrium as shown in the video. The length L of each string is 0,15 meters and the angle theta is 5 degrees. Find the size, the magnitude of the charge on each sphere. Okay, so what are we given? We are given the mass, right? We know that the mass is equal to 3 times 10 to the power of minus 2 kg. We are looking for the charge. We are told that the spheres are identical, so they are either both positive or they are both negative. Either way, we know that since they are identical, they will repel each other. Okay, we know that. We are given the length of the string. L is equal to 0,15 meters. What else? Theta is equal to 5 degrees. But most importantly, we are told that they hang in equilibrium. Okay, so this here will give us an idea of the forces, of how to sketch the forces acting on each sphere. Let's use our left hand side sphere, for example, and sketch the forces acting on the sphere. Okay, so this is our left hand sphere. We don't know yet if they're both positive or both negative, so I'm just gonna leave it blank. I'm not gonna write positive or negative. I'm just gonna leave it blank. And we know that on this sphere there's a tension force resulting from the rope. Okay, so we have a tension force leaving the sphere, tension force as a result of the rope. Okay, and we know that the angle here, the angle here is theta. Okay, what else do we know? We know that this sphere has a repulsion force going to the left as a result of the sphere. Okay, just gonna write here FR. We also know that this sphere has a gravitational force, the weight, okay, FG is equal to mg. And so these are all the forces acting on the sphere, and they tell us that the spheres come into equilibrium when the angle theta here is 5 degrees. Okay, so using that, I'm gonna write down the forces acting on the horizontal direction and the forces acting in the perpendicular direction. But first, before we do that, we have to break the tension force into its vertical and horizontal components. Okay, so the tension force has Tx, and it also has Ty. Okay, and we understand, I believe we understand that Tx is equal to T, which is the tension force, times sine theta. Ty is equal to the tension force times cos theta. Okay, Tx here you can also write as Tx as your Lx, and your Ty you can just write it as your Ly, and T is your L and T is your L. So basically this T is equivalent, the value of this T is equivalent to the value of the L. Okay, I just wrote T to emphasize that it's the tension force, okay, which is equal to the length of the string. Okay, moving forward. So now taking the forces acting in the horizontal components, Fx in this sphere, these are equal to Tx, right? Which is the tension force in the horizontal components. Tx is equal to T sine theta minus your repulsion force, which is going on the left, so it's going to be minus the force of repulsion. Because the sphere comes into equilibrium when theta is equal to 5, I can set this equal to 0, right? Where theta is equal to 5. Remember, it comes into equilibrium, so the forces in the horizontal are equal to 0. Similarly, the forces acting in the vertical direction is equal to your Ty. Ty is equal to T cos theta minus your mg, gravitational force. And that, because the sphere is in equilibrium at theta is equal to 5 degrees, that's equal to 0. And then we can label this as 1, we can label this as 2. And then we can set, using this formula, we can easily see that T cos theta is equal to mg, right? And we can rewrite, which then means that making T the subject of the formula, T is equal to mg cos theta. Okay, then moving to this side, substitute. Okay, I'm going to say this is equation 3. If we substitute equation 3 into equation 1, right? From equation 1, we see that T sine theta is equal to Fr, right? And you substitute your T here, you're going to have mg cos theta sine theta equal to F, the repulsion force. So mg tan theta is equal to Fr, the repulsion force. Okay, so we have our m value we are given. We know that g is 9,8. We know that theta is 5 degrees. And we know that this is equal to the repulsion. Now we know that the repulsion is equal to K. Because the spheres are identical, I'm just going to write K2 square, right? Because they're the same, they're identical, divided by the distance between the spheres squared. Now, when it comes to the distance between the spheres, R, this is the distance between the spheres, we know that for the tension force Tx, right, the distance between, let me just write there, the distance between here and here, this is Lx, right? And the distance between here to here, that is our Ly. Okay, so Lx is the same, as I said, it's Tx. It's your tension force in the horizontal component. So the distance between these two spheres is actually 2 times Lx, because this sphere also has an Lx going in this direction, right? And this Lx of this sphere and this sphere is the same value. It's the same value because they're the same, they have the same charge. The length is the same on both sides. The angle theta is the same. So you have 2 times Lx as your rate as your distance between the two spheres. can rewrite that as K Q square over 2 times Lx. As I said, Lx is equal to Tx, which is this. So you have 2 times this. This is equal to Lx. Tx is equal to Lx. So 2 times T sine theta. That is the distance between the spheres. Okay. Where the T is the same as L. Alright. And then from here, we are looking for Q. So if I want to set this equation equal to this equation, that's what I'm going to do right now. So mg tan theta is equal to K Q squared divided by 2 times T sine theta squared. And then I'm going to make Q the subject of the formula. Q squared is equal to times T sine theta squared mg tan theta divided by K. Then I'm just going to continue this side. You can substitute everything. 2 times T is equal to our L, so that's 0,15. Then our sine theta is equal to 5 degrees. Square that. And then our mass is 3 times 10 to the power of minus 2 kg. Our G is 9,8. Degrees divided by 9 times 10 to the power of 9. That gives us a value of 1. Okay, so Q squared value is 1,9538 times 10 to the power of minus 16 coulombs. Then Q is equal to, taking the square root of that, it's 1,4 times 10 to the power of minus 8 coulombs. That's our answer for this question. So this is the charge of each sphere since the spheres are identical.